Hi, this is Kara Tierney from Monroe Community College, and in this video we're going to continue our discussion on determining molecular polarity, and we're going to do that by just looking at some examples. And so our first example we're going to start with is CO2. And so you might want to refer to the last video. We had a step-by-step of how to determine polarity for molecules. And so I want you to keep that in mind as we're doing this. So the first step is always to draw the Lewis structure. So right now I want you to take a moment. I want you to pause the video. I want you to draw the Lewis structure, and I want you to press play when you're done drawing that Lewis structure. So here's our Lewis structure for CO2. Our next step is we need to determine the molecular geometry and draw the 3D sketch. So I want you to practice that right now. I want you to determine the geometry of this molecule and draw the 3D sketch if it's not the same, and then press play when you're ready to continue to our next step. Okay, the geometry of this molecule happens to be linear, and so we don't need to draw a new 3D sketch because we have this drawn with our 180-degree bond angle anyway. So in this case, we don't have to draw a new 3D sketch. So once we have our Lewis structure and our geometry determined, the next thing we're going to do is we're going to draw our dipoles or our partial charges on this molecule. So I'm going to do this both ways. So the first way I'm going to do this is by drawing our partial charges. So what we need to do is compare the electronegativities for carbon and oxygen for each bond and determine where our partial positive and where our partial negative charge is. When we take a look at their electronegativities, we know that oxygen has a higher electronegativity. So in this bond, oxygen's going to have a partial negative and carbon's going to have a partial positive. In our other bond, we see the same thing. So what we end up with is two partial negatives surrounding our partial positive. We need to look for a way for us to draw a line that would separate the partial positive from the partial negatives. There's no way for us to separate these by a single line. So that means that we have a nonpolar molecule. Now I want to show you how we determine the polarity using the arrow method. So since we determined oxygen is more electronegative than carbon, we can draw those arrows just like that. The arrows pointing out towards the oxygens, the positive towards the carbon. And what we can do is we can think of this one of two ways. We can think of it first as adding vectors. And if you're familiar with adding vectors, two opposite vectors with the same length added will give us no net vector. Or we can think of it as a tug of war. If we think of these two oxygens pulling on that carbon, is there a clear winner here? No, they're both pulling with the same strength because both of these bonds are polar to the same degree. So having no winner for a tug of war or having no net vector are both indications that we have a nonpolar molecule. Let's look at our next molecule, CH2O. So right now, I would like you to take the first two steps. Draw the Lewis structure. Then I want you to determine the geometry and draw the 3D sketch for this molecule. So press pause and press play when you are ready to continue. So here we have our Lewis structure. We see that we do have a double bond between the C and the O. And when we look at our geometry, we have a trigonal planar molecule because we have 3 electron groups and no lone pairs around that central atom. So we have a 120-degree bond angle. When we go to determine polarity, I'm going to do the deltas first and then we'll use the arrows. So we need to evaluate each bond at a time. So let's look at the bonds between C and H. We know that carbon has a higher electronegativity than hydrogen, so we're going to have a partial negative here and a partial positive near each of our hydrogens. And between the bond between carbon and oxygen, oxygen's more electronegative, so that will have a partial negative, and the carbon will have a partial positive. So these two partial charges on the carbon kind of cancel each other out right there. And what we're left with are partial positives on the end near our hydrogen and a partial negative on the end of our oxygen. So we can draw this line between a partial negative area and a partial positive area in our molecule. And so this is a polar molecule because we can draw that division. Let's take a look at how we would determine polarity using arrows. So once again, we're going to look at each individual bond. So between carbon and hydrogen, once again, the arrow is going to point towards carbon, since carbon is more electronegative than hydrogen. So each of these are going to point this way. And between carbon and oxygen, oxygen is more electronegative, so our arrow is going to point towards oxygen. And so if we were to add up our vectors here, we see that there is an overall direction towards our oxygen. And both of these arrows here are feeding into that left to right direction. So these two would cancel out vertically but not horizontally. So we would be left with an overall dipole towards the oxygen of this molecule. We can also think of this as a tug of war. If we have the carbon to oxygen pointing out like this and these two pointing in, which means they're kind of pushing towards the carbon, this thing's going to move. There's not going to be much of a fight here at all. So all of these things lead towards us knowing that we have a polar molecule. Let's look at the next one. And actually for this one, I want you to give this a try the whole way through. I want you to do the Lewis structure, the geometry, and determine the polarity, whichever way you feel most comfortable, before you press play. So press pause right now, try the entire thing yourself, and then press play when you finish or if you get stuck in the middle. So let's do each step together just to make sure we're where we need to be. In our first step, we're going to draw the Lewis structure, which should look something like this. We have 3 single bonds with fluorine, and the bromine also has 2 lone pairs, so it does have an expanded octet. When we look at a molecule that has 5 electron groups and 2 are lone pairs, we see that it is a T-shaped molecule. So we're going to draw that T-shaped molecule. Now this sketch actually shows the lone pairs. We don't need to show those in a 3D sketch, but you can if you want to. It won't affect our decision on polarity because we actually don't consider those at all. We're not going to be drawing any arrows or any partial charges around those lone pairs. We're only going to be looking at the polar bonds within the molecule. So this molecule is a little tricky. And that's kind of why I gave it to you in the video, because I like to throw the tricky ones at you so that the easier ones seem easy when you get to them. So we're going to start with our delta method, and this one is the hardest one to determine polarity. So I'm going to show you why sometimes one method is easier than the other, so if you need to flip between them, you can. So let's designate our delta negative and positive areas for each bond. We know that fluorine is the most electronegative atom, so that's going to be a delta negative in our bond. And what we see is that there is really no clear way to draw one line to differentiate between our partial positive and our partial negative area. However, I want you to see that the way that these partial negatives are oriented is more towards this side of the molecule than this side of the molecule. Okay, this is an uneven distribution of those partial charges. So this actually does result in a polar molecule. So sometimes we can't draw that clear line, but we can look at the relative distribution of partial charges. I want to show you how you can determine the polarity using the dipole arrows, and in this case, it's a little easier to see. So our arrows are all going to point towards fluorine. And you're going to see that these two arrows right here totally cancel each other out. One's going up, one's going down. And that leaves us with one arrow remaining. And so that's going to give us our overall dipole of the molecule. So you can see in this case, the arrows are a much more clear way to determine the polarity, but sometimes the delta method works a little bit better too. So I recommend picking your favorite method, and if you find one where it's a little iffy, maybe try the other method and see if that clarifies things for you. So I want you to try these three molecules by yourself, determine if each is polar or nonpolar. Remember, when you are drawing these, you always want to draw the arrows or the delta symbols on a 3D sketch, not a Lewis structure. It's very important. Okay, and we'll go over the answers in class, but I want you to come prepared and give these a good try so that we can go over any stumbling blocks that you might have along the way. And I'll see you in class.